Okay, let's go over probability 3, chapter 3 inside our unit. So in this chapter, it's basically just about difference equation, random walks, recurrence relation. That's something that shows up almost every year in the exam. So let's go over, basically it's just deriving and solving different forms of first order and second order. So we'll often see kth order linear recurrence relation has the form of this sigma of AJ U something plus j equals f of n. So like it's just a formula of what it should, looks like. Basically, it's like a recurrence where un equals vn plus wn. So where vn is like the particular solution, wn is the homogeneous. So homogeneous basically means we're just setting the right-hand side to be zero and just solving for that equation. And we have most of the time we're not going to get an nth order relation, but rather a first order or a second order, most likely second. So what we have is we have an homogeneous, we find the homogeneous, then for the particular form, we just guess what it is based on homogeneous. Usually we guess the constant. If a homogeneous solution is 1, then we go with Cn, and if Cn doesn't work, we go with Cn squared, so on and so forth. Same with second order with un plus 1 plus aun plus bun minus 1 is equal to fn. So this one only has 1. This one has two extra terms in addition to this one. So that's why it's second order. So a classic example of these recurrence relation difference walks is random walks. So the simplest case we have is basically if you bet, you start off with a certain amount. If you win, you win $1. You lose $1. And your winning probability is P and your losing probability is 1 minus P, and we call that Q. So we often look at what is the probability that you get broke, so the probability of ruin. So for this, we know that we define some notations. For example, UN means the probability of bankruptcy starting with fortune N. So we start off with N dollars. What is the probability that we are bankrupt? UN represents that. So that means that for if we are left with $0, then we're bankrupt. So U0 is equal to 1. That's our boundary on the left-hand side. And then on the upper side, if we have M dollars, then we're just gonna cash out and we just won. So that's like our two boundaries that we establish. And then our recurrence relation happens when our UN is between the 0 and M. And it's basically defined by we have our UN is equal to either we have one case. For probability P, we go to UN plus 1. We win $1, we're $1 richer. Or if we lose with probability Q, we're just $1 poorer. And our UN should be equal to that. So that's where we get our recurrence relation from. And just slightly rearranging that, we get PU n plus 1 minus un plus q times un minus 1 is equal to 0. And then we can just rewrite this as just like substituting it with a different variable. And we solve that and we get that lambda is equal to 1 and q divided by p. So then we just break it down into cases when P does not equal Q and when P does equal Q. Because if P equals Q, then we only have one solution. And if P is different from Q, then we will have two solutions. So that's why we need to separate it by case. If P does not equal to Q, we get UN is equal to this expression here. Technically, it's a good idea to memorize this, but we also need to know how we get it. And I think the major thing is just understanding that it's just solving the recurrence by doing what we know. So we start off with UN is equal to A times 1 to the nth power plus B times Q to the nth power. This is just basically the typical recurrence formula. We got our solution. We just plug it into the nth power times the coefficient. And we're just trying to solve what A and B are. So then we know we're going to solve this by substituting what we know, which is our boundary conditions. We just plug in u0 equal 1 and equals 0. We get these two expressions. And then because they're not whole integer coefficient, we just let a equals 1 minus b from this side. And then we just plug this back into this and we just simplify it to get that b is equal to 1 divided by this expression So then we substitute a back to find that a is equal to that. And we would substitute back the values of a and b back into the original form of this un. We get that un is equal to this formula over here. And then for the other case where P and Q are equal, that means that they're both 1/2. And if it's 1/2, Q divided by P is 1. So then both of our like our repeated lambda would be just 1. So then substituting this in, we know that it has to be in the form of a plus bn because lambda to 1 to the n power is still 1. So we know that it has to be in that form. So then when u0 is equal to 1, we get that a is equal to 1. And when is equal to 0, our boundary conditions, b is equal to -1 divided by m. So then we plug these a and b values back to our original a plus bn equation, and we get that un is equal to 1 minus n divided by m. This expression makes a lot more sense intuitively because the higher our n, the less likely we are to bankrupt, so our un becomes lower. So that makes intuitive sense. Next, other than just like the probability of ruin, we're also curious about the expected duration, like how long our game is going to last. And this is an inhomogeneous thing. So something that we will get is it's basically taking the same approach, and we get that En is equal to this expression over here that we should definitely memorize. And if there are P and Q are equal, then we get this expression. And I'll go through the proof right now, how I got derived it. So kind of like before, I first have to find the recurrence equation. So I know that E of n is equal to either success, which is P times 1 plus E of n plus 1. So I'm one step closer. Or Q, I spin one turn and I also get, so like 1 plus is just basically I take up a turn. And then I either go to the right or I go to the left based on my outcome. So now I simplify that a bit and I get this expression, which is my recurrence. And then what I do next is I have to find, obviously, the homogeneous solution, particular solution. So I get that after plugging this in, I get the roots of 1 and q over p, so it's the same. So either I have to break it down into equal versus not equal cases. And I get that it's in the form of this. My particular inside this, because I have a root 1, that my particular solution can't be 1 or else there'll be repeats. So then I know that my next possible thing is definitely Cn, where C is a coefficient. And then I just put that back into the expression and I get, make sure that here's n plus 1, this one's n, this one's n minus 1. I get that C is equal to this, my Vn is equal to that. Plug it back in, I get my thing. I put in the boundary conditions and I solve that, I get to this expression over here when P and Q are not equal. And if P and Q are equal, which equal to 1/2, then I just plug it into this expression and I get the particular. This time it's n squared because I already have a plus b in form here. So now I have to go with n squared. So for the boundary conditions, and I get to this. En equals n times m minus n. This one is really nice, this form. So it's often used. Okay, moving on. If it's an infinite random walk where we're just concerned with the probability that a random walk starting at n ever hits 0. So it's basically, we can imagine this as if we have a boundary where our lower thing is bankruptcy is at 0. And then we never have an upper bound. So then our upper bound is infinity. So we're just looking at under what situation would we kind of be certain that we're going to go bankrupt versus what is the probability that we're not going to go bankrupt, right? So it's pretty straightforward that if, let's say, P is smaller than Q, then Q over P is greater than 1. So it's more likely that we're going to go down. If we're more likely to go down, then obviously, intuitively, we know that we're going to go bankrupt at some point because even if we go up, the probability of playing infinitely many number of times means that we're going to go down at some point, hit the bottom, 0. So then we're going to go bankrupt. So that's why when we take the limit as m goes to infinity of un, we put it into this expression, we simplify a bit, we see that This goes to zero, this goes to zero, plus one. So we're doomed to kind of bankrupt in this sense. Whereas if P is greater than Q, our UN is this expression as M goes to infinity, this thing tends to zero because it's smaller. And since it's smaller, then we're gonna get that it's at the end, and we're gonna, as we take the limit, we're just gonna approach Q divided by P to the nth power. And if P equals to Q, then we use the previous expression over here, UN equals 1 minus N divided by M. If we take M to go to infinity, we're still somehow doomed to go, guaranteed to hit zero. Because just the random fluctuation would somehow mean that it's gonna at some point hit. So basically, in summary, what we can take away is that if we're doing an infinite random walk, then our probability of being doomed or in a ruined state is if P is greater than Q, then it's Q divided by P to the nth power because it's less and less likely as we get greater. Whereas if it's small, P is smaller than or equal to Q, then we're kind of doomed to become bankrupt at some point. Okay, that's basically chapter three in a nutshell. I think that's the major takeaway. It's pretty different from what you sent me, Kara, on like the questions, but I think I'm gonna just end off this video here and I answer the questions specifically in a different video.